writing section 2.5. Fundamental theorem of algebra. So to start, I want to ask you guys a question, and this will help us out. Is the number 3 is this a complex number? So yesterday we said a complex number. What made a number a complex number? We could write it something with I. So we said a plus bi. So could we write 3 in that form? What? Someone said something that sounded good. 3 plus 0 I. Right? So real numbers are complex numbers, just with the imaginary part being 0. So we can think of real numbers as complex numbers. And the idea here is that the complex numbers are a bigger set. We have the complex numbers and we have the reals. So the real numbers are part of the complex numbers. That's going to be important when we talk about our fundamental theorem. So we can think of any real number as a complex number. So the fundamental theorem of algebra, and I'm just going to write FTA instead of rewriting it. Fundamental theorem of algebra says that if we have a polynomial and our degree is n, so n is our highest exponent. That's fine. N is the highest exponent on our variable. And we want n greater than 0, because if n is 0, it's not a particularly interesting polynomial. What the fundamental theorem of algebra says is that f has at least one 0 in the complex numbers. So any polynomial is going to have at least one 0 in the complex numbers. And we say at least because there can be more. Now, this is interesting. It's a powerful thing. We're going to use it in a little different way. But let's think before we move on. What's the simplest polynomial that would have one 0? What kind of polynomial do we know crosses the x-axis once? Anybody have any ideas? A line, sure. So let's think of an easy line. How about f of x equals, a line crosses the x-axis once. That's a good example. F of x equals x plus 1. So that has one 0, right? The 0 is x equals negative 1. Could we have a polynomial with negative 1 as a repeated 0? In other words, could our 0 have a multiplicity of more than 1? How would we write a polynomial with 1 being our 0, or negative 1 being our 0, but the 0 has some kind of multiplicity? X plus 1, how do we make our 0 have multiplicity? Put it in parentheses. Someone said, someone over here, what did you say? Square it. Perfect. Now it has multiplicity too. So we could think of that 0 as being repeated. We could write it as x plus 1 times x plus 1. Has 1 0, but that 0 can't be repeated. We could put x plus 1 to the 500 power, and then we'd have 500 of those parentheses that we could expand that out when we factor that out. So each of these is a polynomial with 1, 0 in the complex numbers. This one has a repeated 0. It happens twice for our multiplicity. So that kind of leads us into how we're going to use the fundamental theorem of algebra. And what we call that is we've kind of been doing it already, the linear factor theorem. The linear factor theorem, and this is related to the fundamental theorem of arithmetic that we know. We just don't know that we know it. Linear factor theorem says we have this polynomial, f of x polynomial, and our degree is n, and we want n to be greater than 0. We want it to be interesting, more interesting than a constant. When this is the case, f of x has exactly n linear factors, which means we can say f of x equals, we could have some number out in front, some real number, x minus c1, x minus c2, dot dot dot, x minus cn, where the c's are complex. So what the linear factor theorem tells us, coming from the fundamental theorem of algebra, is that no matter what the polynomial looks like, it could be the most complicated polynomial you could think of with 7500th degree and all of these terms and all of these x's raised to the powers. What the linear factor theorem tells us is that we can break it down into these parentheses where all of our factors are linear. So we just have an x minus each one of the roots, each one of the zeros. We can always break it down into a set of parentheses where we have x minus something else, where the c1, c2, cn are complex numbers. And we said real numbers are complex numbers also. So this could be x minus 3, x minus 5, x plus 1, blah, 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 but some of them could be complex. So adding the complex numbers to our real numbers gives us all the numbers we need to completely factor any polynomial, which is a pretty powerful thing. So, sort of related to what we're talking about today, the fundamental theorem of arithmetic. So arithmetic has to do with numbers. When we factor numbers, is there something that we remember about factoring numbers where we end up multiplying a bunch of factors together for a number? Remember doing factor truths, where you take your number and you split it and you branch it all out and you keep dividing. You divide until you can't divide anymore, right? What kind of number do you end up with when you can't divide anymore? What is it? Prime number. This is exactly like the fundamental theorem of arithmetic tells us we can always factor any number into products of primes. We can multiply a bunch of prime numbers together to get any number. This is exactly the same idea. We can factor any polynomial into these linear factors. So these linear factors are kind of like the prime numbers of polynomials. Sort of. Kind of thinking of them kind of the same way. So it's the same idea, and it's the same level of importance to be able to factor our polynomial into these linear factors. This will give us all of our factors, all of our zeros, all of our solutions to our equations, all of our x-intercepts, etc., etc., etc. So it's a pretty powerful thing. And we've been doing that a little bit as we find our zeros, our roots of our polynomials. So we're really not doing anything different than we did the last several days. We're just including our complex numbers in our factors. Now, before we do some examples, I want to talk about the quadratic formula and what happens with the quadratic formula. So our quadratic formula, just as a reminder, is if we have our variables x equals negative b, plus or minus the square root of b squared minus 4ac, all over 2a. And the quadratic formula comes from, you get the formula by completing the square with a quadratic function. It comes from completing the square, which we did at the beginning of the chapter. Now, if we use a quadratic formula and we end up with complex solutions, so the number under our square root is negative. So we get something like x equals, I'm just making this up, negative 2 plus or minus I square root 3 over 3. How are this 2 plus I square root of 3 over 3 and 2 minus I square root of 3 over 3? How are they related? Thinking about what we did yesterday, the day before. I'm going to separate them out. How are those two related? Negative 2 plus I square root of 3, negative 2 minus I square root of 3. Conjugate, perfect. These are conjugates. When we use a quadratic equation and we get an imaginary part here, we get a plus or minus, we always get a conjugate. The quadratic formula always gives us conjugates. It has to happen that way. Our complex roots are always in conjugate pairs. It has to happen that way. That's how they come out. The quadratic formula gives us our conjugate pairs. They always occur in conjugate pairs. So if what we're saying in symbols a plus bi is a 0, a minus bi is a 0. So our complex roots always occur in pairs, and those pairs are always conjugates. So that gives us another little tool to work with when we're finding our zeros of our polynomial functions. Now, let's relate that back to Descartes' rule of signs. Descartes' rule of signs told us the number of possible real zeros, and we said we counted the sign changes, and then we went down, we reduced that by 2. The reason we reduce it by 2 is because the complex roots occur in pairs. I can have 2, I can have 4, I can have 6. So with Descartes' rule of signs, that's why we reduce the number, we can say 2 or 0, 4, 2 or 0, 5, 3 or 1. We have to reduce it by 2 each time, because if we have complex roots, they occur in pairs. We could have 2, we could have 4, we could have 6. So that's why Descartes' rule of signs works the way it does, because our complex roots always occur in conjugate pairs. We're kind of tying all these things that we've talked about in the chapter together. Quadratic formula comes from completing the square, which has to do with the vertex form. Descartes' rule of signs has to do with these conjugate pairs. It's all related. All right, questions on what we've done here? All right, so what I want to do is just go through a few examples of how we are going to use this information and add that on to what we already know about finding zeros of polynomial functions. So let's say our question says, we want a 4th degree polynomial with zeros 0, 1, and 2 minus 3i. So we want to write this 4th degree polynomial. Well, how many zeros should we be able to find for a 4th degree polynomial from what we just talked about? 4, right? 4th degree polynomial, 4 zeros. Now, it could be repeated. You could have a repeated 0, but we should be able to find 4 zeros. So we have 3 of them. What's the 4th one going to be here? 2 plus 3i, the conjugate of this. 2 plus 3i is a 0 also. So we could say f of x equals, and now we're going to use what the linear factor theorem tells us. If x equals 0 is a 0 of the polynomial, what's one factor of our polynomial? The 0 is a 0 of the polynomial, so what that tells us that x minus 0 is a factor, right? I can just write x minus 0 is x. For x equals 1, what's going to go in my other parentheses? X minus 1. That's going to be our other factor, x minus the 0. And then for my complex zeros, x minus 2 minus 3i. And for the 4th factor, the linear factorization theorem says I should have 4 factors. X minus 2 plus 3i. I just write in parentheses x minus each one of my factors. That would be a 4th degree polynomial. I wouldn't make you multiply it out. Just technically, to be a polynomial, it has to all be multiplied out. If I ask you this question, this would, to me, that shows me that you understand that we can write our polynomial this way. I could multiply it all out and get a 4th degree polynomial. And because these two are conjugates, when I multiply this all out, the imaginary parts go away, and all I'm left with is real numbers in front of all of my x's. So we know our complex solutions occur in conjugate pairs, and then we can write our polynomial in factored form. We would also call this factored form or completely factored form. All right, questions there? All right, let's find all the zeros of a polynomial. We want to find all zeros and write in factored form. So we have x to the 4th minus 3x to the 3rd plus x minus 3. So there's our polynomial. We want to find all the zeros and write in factored form. So what do we, how do we start? What do we do? How do we go about finding our zeros? P's and Q's. So this one's nice. This one's nice, right? What are our possible what are our possible rational zeros using our P's and Q's? Since our P is 3 and our Q is 1, and each of those prime, we don't have very many. What are our possible zeros? Plus or minus 1 and plus or minus 3. Those are the only possible rational zeros. Let's try to reduce our work a little bit. Descartes' rule of signs. How many sign changes do we have here? 1, 2, 3. 3 sign changes. So we have 3 or 1 positive. And if we write f of minus x using Descartes' rule of signs to reduce our work, I get x to the fourth. We change the sign on the odd powers, plus 3x to the third minus x minus 3. So how many sign changes do we have here? 1. 1 sign change. That tells us we have one negative. So which one would be easy? Which one would be an easy one to test? Which negative possibility would be easy to test? Negative 1. So let's test negative 1. F of negative 1. I'm just going to plug that in. Change the signs on the terms with the odd exponent. So 1 plus 3 is 4. Minus 3 is 3. Minus 3 is 0. So that's 1, 0. And this Descartes' rule of signs says that there's 1 negative. So all the rest that we have to test have to be positive. So what's the only other possible one? What's the only possible rational zero that could be left? What do we have left? 3 or 1? We could test 1. F of 1 equals 1 minus 3 is negative 2. Plus 1 is negative 1. Minus 3 is negative 4. So positive 1 is not a possible rational zero. So what does that leave to test with synthetic division after we do the synthetic division with negative 1? 3. The only other thing we can test is 3. So let's do our synthetic division now. We're going to set that up, negative 1. We're going to do a 1, a negative 3, put in a placeholder for the x squared. 1, negative 3. Our zero better come out, or our remainder better come out to be 0. What's that? Which one? We're going to do negative 1 first, since we already know that gives us a 0. And then we'll test 3 with synthetic division. Okay? So what do we get? Negative 4, 4, 4, negative 4, negative 3, 3, 0. And the only other possible positive 0 is 3. That would be nice if that worked out. So I'm going to do that right there. 1. 0. So that turns out to be a 0. So 2 of our zeros are, I'm going to list them over here, zeros. X equals negative 1 and x equals 3. And what does this tell us we're left with? Started with a 4th degree polynomial, divided once, divided again, so I end up with a quadratic, right? Go from the 4th to the 3rd to the 2nd. So I have x squared minus x plus 1. Does this factor?
So
Yes. Sure, yeah, it would come out the same. Doesn't matter what order you use. All right, so does this thing factor? No? So what do we have to use? Quadratic formula. So we plug that into the quadratic formula. X equals 1 plus or minus the square root of b squared 1 minus 4ac minus 4 all over 2a, 2. So I get 1 plus or minus, this is negative 3, I square root 3 over 2. So I get my complex solutions in pairs. So these are my other zeros. And then I can write my function, my polynomial, in factored form. So this would be x plus 1, x minus 3. I'm just putting x minus each of the zeros. X minus 1 plus I square root 3 over 2. Hello. Thank you. This is the pen. And then finally, x minus 1 minus I square root 3 over 2. So that would be my polynomial in factored form. And I'm just going to move this so it looks a little. There we go. Yes.
How come the last one is negative x minus?
Oh no, that was just. This is just a little. That shouldn't be negative. That was just a little dot that I put there by accident, just with the pen. So that shouldn't be negative. Questions there? So pretty much exactly what we've been doing. Yes.
The very last one is a 0 to
Just
1 minus I square root 3.
yes. Yeah. So we get the plus or minus tells us we have 1 for the plus and 1 for the minus. Yeah. All right. Let's look at another example. We want to find all the zeros of x to the 4th minus 4x to the 3rd plus 12x squared plus 4x minus 13. And we know that 2 plus 3i is a 0. So we have this 4th degree polynomial. We should be able to find 4 zeros, correct? It might be repeated, but we should be able to find 4 of them. We know 1. Can we find another one really easily? What's another 0? Conjugate, yes. So 2 minus 3i is a 0. Now, before we start through this, let's think through the problem a little bit, so that we get to what I want to show you with this one. So from here, if we know these two are zeros, we know that this would come from a quadratic equation. What if all 4? So before I do that, how would we go about now trying to find the other two zeros? What would we do with this polynomial? What's our standard procedure? Our P's and Q's, yes? Do our P's and Q's synthetic division? How many times would we have to do synthetic division in order then to be able to use the quadratic formula to find two more complex zeros? Twice. We have to do it twice. We need to reduce the power twice. What if this has no real zeros? What if all of them are complex? So we tested, this one would be easy to test, plus or minus 1 and plus or minus 13. What if all of them turned out to be complex? None of the plus or minus 1 and the plus or minus 13 didn't work. What could we do? How could we find the other two zeros if all we know are these two? Long division. That's perfect. And the way we figure out what to do long division by is we know that x minus 2 plus 3i is a factor. And we know that x minus 2 minus 3i is a factor. Those are two of the parentheses. Well, then doesn't that tell us that if we multiply these two together, that thing multiplied together also has to be a factor? So if we know that, say, 30, we know that 3 and 5 are factors of 30, right? What else does that tell us is a factor of 30? 15. 3 times 5 is also a factor of 30. This times this is also a factor of this polynomial. If we multiply this out, we would FOIL this. Multiply this, 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 and then we end up with multiplying the conjugate. So if we multiply this out, I'm not going to go through all the steps, but we would just FOIL this out and simplify. This turns out to be x squared minus 4x plus 13. This has to be a factor of our original polynomial. So then, like Matthew says, now we can do long division. So I'm going to divide the polynomial by x squared minus 4x plus 13. It looks intimidating, but it's really not that bad. And now for this long division, I say, what do I have to multiply x squared by to get x to the fourth? X squared. I multiply each of these, so I get an x to the fourth minus 4x to the third plus 13x squared. And then I'm going to subtract. That goes away. That goes away, and I get 12 minus, that should be a 13x squared, 12 minus 13x squared. I get a minus x squared. Because I have 3 terms out here, I need to have 3 terms down here to divide, so I'm going to bring down the plus 4x and the minus 13. Now I say, what do I have to multiply x squared by to get x squared? Sorry, not x squared. What do I multiply x squared by to get negative x squared? Negative 1. Multiply. Plus 4x. Minus 13. Subtract, and my remainder comes out to be 0, because it is a factor. So that tells me that this x squared minus 1 is the other factor. Well, now we're done, right? So if x squared minus 1 is our factor, x squared minus 1 equals 0. It's going to give us our zeros of our function. X squared equals 1, and x equals plus or minus 1. So this one, they did turn out to be real, but if they had both turned out to be complex, this is the method we would have had to use to find them. So here are our zeros. 2 plus 3i, 2 minus 3i, and plus or minus 1. So this one we could have tested plus or minus 1 and seen that they were zeros. If it turned out that those were not zeros, that all four were complex, we would have had to do this. Yes, no.
If FOIL constants together,
So that would work. We could. So what we would have to do. So Matthew's question is, why couldn't we just do long division? We'd have to do long division by x minus 2 plus 3i. So we would have, instead of this, we'd have x minus 2 plus 3i. So we have those imaginary numbers in our long division. You could do it, but it would get kind of messy. It is possible to do. And then you would have to do the long division by the other factor to get us down to a quadratic. You'd have to do it twice to get from the fourth degree to the second degree. But it would work. It would work. All right, questions on that example? All right, we're not going to go all the way through this next one. I just want to show you how to set it up. There are a couple of homework problems that are like this last one. We want a cubic polynomial. With our zeros 3, 2 minus the square root of 2i, and let me write that, 2 minus I square root 2. And we want f of 1 equal to 6. So we have some restriction on our polynomial. All right, cubic polynomial, how many zeros should it have? 3. What's another zero that we can figure out? 2 plus I square root 2. So 2 plus I square root 2 is a 0. So now I'm going to use these zeros to write f in factored form. And I'm going to say f of x equals, let me go back here really quickly. Remember we have this a out in front, possibly out in front when I factor this polynomial. I need to put that in here. A times x minus 3 times, I'm going to write this in factored form, x minus 2 minus I square root 2 and x minus 2 plus I square root 2. And then we have this piece. This is what we're going to use to find a. So this tells me when I plug in x equals 1, f of x has to equal 6. So I say 6 equals a. We don't know a yet. 1 minus 3 is negative 2. X is 1. We're plugging in x equals 1. 1 minus 2 minus I square root 2. And 1 minus 2 plus I square root 2. And now I multiply this out and solve for a. So I've FOIL this out first, multiply by negative 2, and then you get a 6 equals a times some number. And then you divide 6 by whatever that number turns out. And that would give you a. So then that would let you write your polynomial out like so. So I think there's 1 or 2 problems in your homework that are like that. Yeah, so you would what I would do is distribute that negative 1, simplify those parentheses, and then you'd FOIL that parentheses. So it's like what we did, some of them we did yesterday like that where we FOILed. You just end up FOILing. All right, homework. I changed the homework up a little bit from what's on the board. every other odd. And for this, we want to skip number 29. Because on number 29, one of the zeros turned out to be 5/3. 51. There we go.